shortening estimate of post-tensioned members. First, why is it of specific value, importance to talk about shortening of post-tensioned members? All concrete members shorten, shrinkage being the largest component. The question is, the shortening does not have a significant impact in the performance of conventionally reinforced concrete, but it does in performance of post-tensioned members if it is not recognized in design and not allowed for. One of the presentations of this series specifically addresses the consequence of not allowing for shortening in post-tensioned members on the performance, specifically the capacity, load carrying capacity of a post-tension member. Now, in this presentation, I present to you the amount of likely shortening and how to estimate it. In other presentations, it is covered how to take care of it. Now, let us start. The presentation starts with an overview, computation of shortening, and it specifies that it is due to shrinkage, creep of concrete, elastic shortening, temperature effects, and follows it with an example of shortening calculation. The example takes a couple of pages, but if you do not want to go through those pages, you use just an estimate, a rough estimate without calculation. That is engineers' long-term shortening estimate. And then in addition to shortening estimate, you may need to know how much shortening is going to take place over a length of time. Since in your design to allow for shortening, you will need to know the allowance to be made for how many inches or how many fractions of inches or millimeters, and that is in the last item is the engineer's shortening. Now, concrete shortens primarily due to shrinkage. By the way, the image on the right shows how certain column reinforcement is blocked so that the concrete around it would be allowed to shorten and not be obstructed by the column reinforcement. Now back here, concrete shortens primarily due to shrinkage. Post-tensioning concrete shortens more because of pre-compression that is applied at post-tensioning. Preventing shortening leads to shrinkage cracks. Shrinkage cracks are essentially not detrimental to the safety of conventionally reinforced cracks, not detrimental to conventionally reinforced members. But shrinkage through cracks are detrimental to the safety of post-tension members as they reduce the member's moment capacity. Now, why and how? At the bottom it says on presentation 13, the focus is on the impact of shrinkage cracks on the moment capacity of post-tensioned members. So in design of post-tension members, it is critical to recognize the required shortening from post-tensioning, to recognize it and to allow for it in your detailing. And then there is the engineer's estimate that will be offered at the end of this presentation. Now, coming to computation, shortening is caused by shrinkage, creep, elastic shortening, and temperature. There are rigorous procedures to estimate the shortening from each effect. ACI has a special publication. European Code EC2 also has special publication to determine in detail the amount of shortening. But in engineering design, in our everyday work, an approximate method is used, and the effect of each of these parameters like creep and shrinkage is assumed to be independent from the other. Let us see whether this can be pushed up there. Good, it's better. Now, the following presentation is an streamlined version intended for use in engineering offices. The material is based on the following assumptions, on the following data. The effect of each of the elements that cause shrinkage is independent from the other. In other words, we are assuming that shrinkage shortening does not impact creep shortening and so on. That simplifies the presentation. The effect of each is independent from the other. And the parameters given in the following are based on this concrete block or concrete material. This is the weight of it, this is the strength of it, and this is the average pre-compression. Now, if what you're using is different from this, which mostly will be, in the following there are instructions how to take care of the variation. So shortening A is length times shortening per unit length of elastic shortening, shrinkage, creep, and temperature. This is the relationship we use. The creep and shrinkage values obtained through laboratory tests are referred to basic shrinkage here and basic creep. We start from a basic shrinkage and basic creep, which is determined from laboratory tests, and modify them for our project if the parameters of our project are different. Shrinkage is caused by loss of moisture from concrete and chemical action of water with contents of cement. Shrinkage is considered to be independent by applied stress, nothing to do with loading. Shrinkage is the largest contributor to the shortening. In the absence of laboratory tests or code recommended values, the base shrinkage strain is assumed to be between 500 and 600 microstrain. That is times to the minus 6, 10 to the minus 6, the microstrain. This is for water cement ratios 0.4 and 0.5. Now, if the condition you are dealing with is different from the standard lab, then you adjust the shrinkage of your condition by these parameters. This is the standard shrinkage value. There will be an adjustment for relative humidity of your project, and there will be an adjustment for the dimensions, water to surface ratio of a volume to surface ratio of the project you have. For humidity, depending on the ambient humidity, the shrinkage value calculated will be multiplied by these coefficients. For 100% humidity, there will be 0 shrinkage. Typically, the values are calibrated for 70%, for which the modification will be 1, so in effect, no modification. Members with higher volume to surface ratio lose less moisture. The smaller the surface in relation to the volume, the less will be loss in moisture. Use the following relationship to adjust the volume to surface ratio of the member you are dealing with. Now here is the coefficient volume to surface ratio, depending on whether you use the US or SI system of units. The surface area used in determining the volume to surface area should include only the area that is exposed to the atmospheric drawing. For poorly ventilated locations, use 50% of the interior perimeter. Now let us look at this example. Here is a slab. For this slab thickness H, what would be the volume to surface ratio? Obviously, the volume for a unit length of the slab is this, length times height, and the surface will be 2 times the exposed region. So it will be H over 2. That's what will be. Now, in this case, a volume to surface ratio will be a little bit different. Volume is the hatched area. These are the dimensions. And the surface will be the perimeter around it. So the volume is the hatched area, the surface, the perimeter, and the volume to surface ratio will be this. Now we come to creep. Creep is taking place under sustained compression. The magnitude of creep is generally between 1.5 to 4 times the initial elastic shortening. 2.5 is really the common value. The base creep generally used is assumed to be 2 times the elastic shortening. The applicable creep coefficient for each instant is arrived by modifying the base creep, the value 2, by the conditions of the project at hand. So this is the actual creep value for your project. This is the value of standard creep 2, and these are the coefficients by which the creep for your project will be adjusted. This is based on average precompression. The more the precompression, the higher the creep. Based on concrete strength, there will be a modification. Humidity is the next modification, and volume to surface ratio also impacts the creep value. So the final creep coefficient will be the basic creep value times these adjustments. The correction factor is 1 for the average precompression around this range. Now, other coefficients are given here. Kc here, the value of Kc is obtained from these expressions. The elastic shortening is immediate response under compression, the shortening under jacking force. The average strain from elastic shortening, is the precompression, that is the precompression divided by modulus of elasticity. That is the strain, initial strain from application of the force. When tendons are stressed one after the other, as is the common case in slab construction, the force in previously stressed tendons will decrease as subsequent adjacent tendons are stressed, which leads to elastic shortening of the member. Now, when you stress subsequent strands, you compress the slab, so the tendons which were stressed before are likely to lose slightly their precompression. The relationship is based on average precompression. It is not necessary to adjust for this. Now, why it says here you need not make any adjustment even though you know it? Because the expression which is derived is based on final average precompression long term when every strand is stressed. The elastic shortening, it depends on the modulus of elasticity of the concrete. And the modulus of elasticity, depending on which system of unit you use, is given by these relationships. The ACI 318, it depends on the concrete's compressive strength at time of stressing. But you may not know the concrete strength at time of stressing. There is a relationship that you can calculate it. We will get to that. Most projects specify the minimum concrete strength before it can be stressed, and that is the initial compressive strength at stressing. If not available, then you use this formula that the concrete strength at stressing is a fraction of the concrete strength on day 28, on the specified. This is the specified concrete intended to represent day 28, and this is the concrete strength when you stress. Now the parameter here is day. T is day. On day 3, then you put day 3 here and you find what the stress is likely to be. Temperature effect. Now, by the way, this image on the right shows provision made for the slab here supported over the wall to be moving over the wall when the strands are stressed. The bond breaker here you see over the wall allows the slab to move, and the rebar going from the wall below to the wall above is covered in a compressible substance. so that it will allow the slab to shorten when stressed, but keeps the continuity of rebar from below going to the top. The temperature effect, coming back to the temperature effect, is length of the member times temperature times coefficient of thermal expansion, and the coefficient of thermal expansion is given here for concrete, depending on which system of unit you use. Now we went through the individual components of shrinkage, creep, temperature, and elastic shortening. Now we go through a numerical example which integrates all these together. In this example, this is the material property, and we assume the length of the member is around 30 meters, 100 feet. Required, estimate the long-term shortening of the member if it is allowed to shorten unrestrained. Now we start with the base shrinkage of this value, base creep here, and calculate the elastic shortening using this standard formula. The concrete strength at time of stressing is given by this formula. We stress it on day 3, so I substitute on day 3 and find the concrete strength on day 3 to be this much less than the 28 days. And the modulus of elasticity at the bottom left uses the formula, and this is the modulus of elasticity. So elastic shortening will be for force divided by area, which is stress over modulus of elasticity. That is the elastic shortening. Strain, shrinkage, this was the formula, and we assume we are at 75% humidity. Calculate the adjustment due to 75% and the coefficient required for adjustment due to humidity. Coefficient required for adjustment due to volume to surface ratio of the member. The member was a flat slab construction, 8-inch thick, so the volume to surface ratio of it will be this. So the correction due to volume to surface ratio given by this formula, and the shrinkage therefore will be this much, going through the numerical work. Now, correction to concrete strength, or concrete strength specified in the example is 5,000 psi. The standard test was 4,000, so we will make a correction due to that also. Correction due to relative humidity, we had it. And now volume to surface ratio for creep. Volume to surface ratio is half thickness, 4 inches. Correction factor for it given by this relationship, putting the numbers in the relationship we had for creep. So the creep coefficient will be 1.49. Total shortening is the length of the member 100 feet times the sum of elastic shortening, shrinkage, creep. I have left the temperature out because that varies much. Temperature effect separately is this much. This is all the others and this is the temperature effect. So the total will be 0.84, including the temperature, 0.84 over 100 feet of slab, including temperature. Now, that goes through the simplified example. Often, during the design, one does not have enough time, or does not, I should say, dedicate enough time to go through the detailed calculation, even though what I just presented is very much simplified by alternative, compared to alternative, more involved methods. You need to know the shortening during the design time in order to evaluate the details of connection of the post-tension members to their supports, walls, and columns. Why do you need to know that? Because depending on the detail and the amount of post-tensioning that you may lose to the supporting members, you impact the safety, the bending capacity of the post-tensioned member. I should say the bending capacity of the post-tensioned member. So you need a quick and rough estimate. For preliminary design of common building construction in California, the post-tensioning design engineers start with the following assumption for the total shortening of a post-tensioned floor slab. The assumption is based on observation and preliminary calculations. The preliminary assumption is often used to detail the member connections for the anticipated member shortening on the jacking force. So the assumption, the calculation, the estimate is intended to be used for detailing of the project. Now this is the assumption to start with. For every 100 foot, the long-term shortening of the slab is assumed to be 3/4 of an inch. This translates to 6.3 millimeters for every 10 meter of a floor slab. Now, this is the total, but if you want to have the detail developed such that it will allow certain amount of shortening and the members will lock together, you need to know a short-term amount of the shortening. Often in design of post-tension floors, the construction is detailed and scheduled to allow a portion of the members' anticipated shortening, the 3/4 per 100 feet, to take place before the member is locked in position for the remainder of the construction. The detailing of connections for temporary shortening requires the knowledge of members shortening over a short length of time. This ACI code gives you the estimate of member shortening. The common practice is to estimate the long-term shortening and refer to a graph for estimating the fraction rather than going through the detailed calculation of ACI. The graph of the following page uses the ACI values for a standard concrete mix and condition. Your condition might be a little different, but this is the graph which is says on day 20 the percentage of shortening is about maybe 35%, something like this. Or on day 15 it might be 30%. So this is the graph you would be using, which is based on the cylinder test in the lab used to derive ACI and applies to these conditions. Your condition might be a little bit different for a given slab thickness, concrete strength, and stressing for at a given concrete strength, modulus of elasticity, again pre-compression 150 psi, assume the creep coefficient and shrinkage values and ambient humidity and so on. Member moist cured for 3 days. Now, how reliable and how accurate is going to be correlation of your project with this is questionable. It just gives you a sense of a range of numbers, and you really have to recognize that there will be shortening and you have to allow for it. The exact amount is a rough guess. And this is the standard cylinder stressed on day 3. That is where the relationship of the previous page comes. So in summary, this is, by the way, on the right, typical shrinkage crack in a post-tension member. It is a through crack. By that I mean goes through the depth of the member and impacts its pre-compression from one side to the other because there is no bond between the two. Loss in pre-compression translates to loss or reduction in moment capacity. That is explained in another presentation. We went through the overview, went over shortening calculation due to shrinkage, creep, elastic shortening, and temperature effect, did a numerical example, and came up with the long-term engineer's estimate of shortening and short-term shortening using the ACI curve. Thank you. The presentation I made here was based on information extracted from the book shown on the right. Thank you.